Proportions are something we're struggling with, it seems. They are calculated by taking some count of success x over n trials. So success over trials. So it's a fraction, but more often than not it's given as a percent or a decimal if it's calculated for you. If it's written in a statement, it's probably going to be something like 15 out of 20 people like peanut butter. So 15 out of a random sample of 20 people prefer peanut butter over Nutella, perhaps. I don't know. Okay, so symbols. Proportion. Population proportion. Sample size. And sample proportion. So we're talking about two samples, so proportions 1 and 2. The population proportion is going to be P1 and P2. The sample size would be N1 and N2. And the sample proportion, P hat 1 and P hat 2. Conditions. Let's start with SRS. Both samples can be viewed as SRSs from their respective proportions. I'm sorry, I said proportions there. It should be populations from their respective populations. Cram that in there. Normal. N1 times P1 has to be greater than or equal to, what do you think? 10 is what it has been. This changes because we have two proportions. It's 5. I don't know that I can give you the rationale for that, but so N1 times 1 minus P1 also has to be greater than or equal to 5. N sub 2 times P sub 2 greater than or equal to 5. And N sub 2 times 1 minus P sub 2 also greater than or equal to 5. So I guess the 10 is there, it's just combined between the two proportions. Independent? The two samples are independent. That's necessary. also our population, our respective populations in regard to our sample size. We still have to have populations that are at least 10 times as large as our sample. And we get to learn a new letter here. P hat C. P hat C is our combined sample proportion. What it is when we put our P1, P hat 1 and our P hat 2 together. So this is the count of successes in both samples over the count of individuals in both samples. I'm going to change that to trials because it may not be individuals. It's easy enough to calculate. It's x1 plus x2 over n1 plus n2. Alright, so what do we do when we have two things? We compare them, right? And we have learned that we have two basic methods of comparing, well, one basic method of comparing things and another one looking for intervals. So let's, if everybody's with me, let's get on to our formulas. I still see a couple people writing. Alright. Okay. So, our confidence interval. For two proportions, looks like this. P hat 1 minus P hat 2 plus or minus Z star. Remember, with proportions we have a way to identify a normal situation, so we can pull off table A, so we don't use t's at all, times the square root of P1 times 1 minus P1 all over N1 plus P2 times 1 minus P2 over N2. It is likely that we won't have p-values on only p hat. So if P1 and P2 are not known, meaning they'd be given, substitute P hat 1 and P hat 2 respectively. Okay. Standard error. of p hat 1 minus p hat 2 equals, so the difference in the standard error difference in the two is a square root p hat 1 times 1 minus p hat 1 over n1 plus p hat 2 times 1 minus p hat 2 all over n2, which is this thing only with the p hats as mentioned. That's the standard error of the difference of the p hats. There's another calculation for this. I don't know that it's necessarily easier, but this is another way that you can get this. It would be p hat c times 1 minus p hat c, that's the combined p hat, times 1 over n, 1, plus 1 over n2. That all looks quite lovely, doesn't it? Okay. We've got one more to talk about real quick, and then we're going to talk about the shortcut for this. Significance test. That's our standardizing for two proportions. The null hypothesis is going to be P1 equals P2. The two proportions are equal. The alternative hypothesis is going to be that they're not. It is either greater than, it's less than, or it is not equal to P sub 2. The z-score for this is p hat 1 minus p hat 2 over this guy right here. P hat c times 1 minus p hat c times 1 over n1 plus 1 over n2, which is also this. So what usually happens about this time, especially things that we've sort of struggled with proportions in the past, is that this is the sort of the breaking point. If you haven't already had it before, this is the breaking point. This is where you as the student go, okay, I'm done. In most cases, okay? The good news is this. Let's go shopping in the calculator for some help here. Okay? Go to Stat, Tests. The first one, let's talk about this guy up here first, the confidence interval, the 2 prop. So it's going to be one of the tests that's below this. It's below 7. So we're looking for a 2 proportion z interval, and there it is, a 2 proportion z interval. So I'm going to write this over here as 2 prop z int. That is going to be your best friend. Now if you go ahead and click on enter, you'll see that it only asks you for 5 things. It asks you for x1 and n1. It asks you for x2 and n2. And then all it asks is what confidence level do you want? So you literally just have to put the two fractions in, and it does everything else for you. So, never fear. I feel the need to give you this because, well, because you guys are stats students and in AP, but the reality is this guy is going to save our bacon on these problems. Okay. Now, what if we go shopping for a significance test? Do we have a significance test for two proportions? Yes, we do. Right here at number 6. A two proportion z-test. I'm going to click on that just to see what sort of craziness it asks for. It asks for the top of the fraction and the bottom of the fraction on the first one, top of the fraction and the bottom of the fraction on the second one. What kind of test we're going to do, whether the x1 and the n1 fraction is greater than, less than, or are they not equal to. You have to answer whether you want blue or some other question, right? And you tell it to calculate. So, I'm trying to make a little bit of light of all this, but this is simply just the two-prop z-test. Now, what you could be asked for on a test is what's the standard error of p hat 1 minus p hat 2? And I don't know that you would get that kind of a question, just that part, on an AP test. Again, knowing that we can use the calculator, as long as we're writing everything down that we put in and get out, you're good to go. Okay. So let's look at a problem. On page 812, I'm going to look at a Lyme disease problem. So this problem says, it's 1325, Lyme disease. It says, Lyme disease is spread in the northeastern United States by infected ticks. The ticks are infected mainly by feeding on mice, so more mice results in more infected ticks. The mouse population in turn rises and falls with the abundance of acorns, their favorite food. Experimenters studied two similar forest areas in a year where the acorn crop failed. They added hundreds of thousands of acorns to one area to imitate an abundant acorn crop, while leaving the other area untouched. The next spring, 54 of the 72 mice trapped in the first area were of breeding condition, versus 10 of 17 trapped in the second area. Okay, so 54 of 72 in first area, and 10 of 17 in the second area. Construct and interpret a 90% confidence interval for the difference between the proportions of mice ready to breed in good acorn years and bad acorn years. Follow the inference. So this is the supplemented group. These guys got the extra acorns, and these guys were out of luck. These were no luck Charlies. Okay, no luck Charlie, right? Okay. So this is going to be my x1, n1, and x2, n2. We probably need to check our conditions. I tend to get lazy about that, and that's a bad thing. So, SRS. What have we said about collecting specimens from the environment as far as being an SRS in the past? Nobody remembers this? I've talked about this a number of times. You go out and you dig earthworms out of your backyard. You can consider that an SRS of earthworms from Boise, okay? Even though they just came out of your yard. So, assume, it's reasonable to assume specimens collected from the environment or from nature are random. So anytime it's something collected out of nature, some biological specimen or something like that, we're going to call it an SRS. Independent. Do you think one mouse is independent from another? I'm thinking, yeah, mice are independent. Assume mice to be independent. Normal. Here's where we need to make some calculations. We haven't said what p hat 1 and p hat 2 are. So p hat 1, I'm just going to write that over here on the side. P hat 1, that's the supplemented group. That's going to be 54 out of 72. So 54 divided by 72 is 0.75. And p hat 1 is 10 of 17. That's about 0.5, I'm going to call that 0.59. 0.588 is what I get. 0.59 is close enough. So we have to double check our sample size and our proportions. So we're going to say N1 times P hat 1. I don't have P, so I substitute P hat. So is 72 times 0.75 greater than or equal to 5? I think yes, 75% of 72 is definitely greater than or equal to 5. How about 72 times 1 minus 0.75? Is that also greater than or equal to 5? And that will also be greater than or equal to 5. So those are met. We've got to check the second proportion though. Is 17, how many mouse I found in the No Luck Charlie group, times 0.59, is that greater than or equal to 5? I believe it is. And is 17 times 1 minus 0.59 also greater than or equal to 5? So is 40% of 17 greater than or equal to 5? It is. So our conditions are met. Now we can do our calculation. It's a confidence interval. So we are going to use our test in the calculator. We want, it's actually not a test, it's an interval, right? We want the 2 prop z int. So I'm going to say over here, 2 prop z int, and x1 54, n1, I'm sorry, oh yeah, no, it is 54. Something got changed in I'm looking at the calculator. 72, so I'm going to put those in. x2 would be 10, and n2 is 17. Confidence level, let's see, they want 90%? 90%, yeah. So all I need to do is change that 95 to a 90. What? What? $54. Oh, where did my numbers go? Thought I put those in. There we go. So what we get is negative 0.0518 to 0.37529. P hat 1 is 0.75, which I already have written down. P hat 2, 0.588. And I've got the N1 and the N2, I think, already. Here's a problem. We're talking about mice here being a breeding condition. Do you think it's reasonable that I have a negative value of mice that are in breeding condition? No. So what do we do with that? Any thoughts? 0 is a solid thought. But let me ask you this. Is it reasonable to think that in a group of mice that there are going to be 0 that are in breeding condition? I mean, unless there's some massive disease or something like that, which we're talking about that, we are. But that's not likely either. So whenever we get a negative situation in this case, we actually take the absolute value of that. So we're going to say that we are 90% confident the true proportion of mice in breeding condition, the true difference in proportion, I should say, of mice in breeding condition so we're talking about proportion here, so we're going to say is between 0.05 and 0.375. Or you could say 5% and 37.5% if you wanted to do that. That would be just fine. Okay.